All right, so what I want to do today is kind of go through solving some more 2D equilibrium problems. Okay, this is the heart of statics. Like this is the key stuff. All right, this is the key stuff. This is really where we got to get into it. Okay, this stuff, and then when we get to the 3D stuff, which is coming really soon, this is the key stuff. But that means that I'll spend more time on it. Okay, I'm not going to try to fly through anything. We're going to try to go through it slow. Okay. So this is really important. That's why we want to kind of get into it. Remember, with 2D equilibrium problems, when solving the problems, you have three equations. Sum of forces x, sum of forces y, and sum of the moments about some point. I say A, but it's not really A all the time. I mean, there's nothing special about point A. It could be another point, right? Okay, you can sum moments about pretty much any point, and it's equal to 0. Okay? So let's take a look at this problem here. It says here, determine the force in the cable in order to lift the 200-pound ramp. Okay? And just notice a little bit carefully here. It doesn't say this, but it sure looks like the ramp is pinned at A. If you look at the pin there at A, that sure looks like a pin to me. It doesn't say anything about where the ramp is at B, but we haven't learned friction or anything like that, so it looks like a smooth surface to me, kind of like what we looked at last time. It doesn't say anything about C, but I mean, it looks like there's a rope pulling on C, right? And G, point G there in the middle, that's where you would put the force, the weight force, right? Because that's what we call the centroid. Okay, we'll actually learn about that a little late in the game, late in the class, right? We will learn how to find the centroid. For now, we just give it to you. Hey, centroid right there. Of course, we would normally assume the centroid to be around the geometric center of an object. That's not always the case, okay? But it's, that's where it is in this case. And point D is just where the spool is or whatever pulley is that's holding it up. Okay? So we have to figure out the force in the cable that's obviously pulling at C. So we have to draw a free body diagram. And really this problem, the biggest thing is drawing the right free body diagram. And it's really easy to draw the wrong free body diagram and get stuck. Okay? So we first start and we go, okay, well, I see the lift here, A to B. So what I'm going to do is I'm going to draw something like that. If you want to put some thickness on it, sure, I don't care. Draw it like that. It doesn't matter. Now, do I have to draw the rails or whatever it is, the handrails? No, not really. I mean, if you want to, you could draw the whole thing, but you're just wasting time. I mean, really, it's just that, right? Now, the first thing I do is I look at everywhere where it's touching. Okay, where is this thing touching? Well, I know it's touching at A, and so it's a pin force. I think it's a pin force, so I'm going to have AX, AY. I know it's touching at C, so I'm going to draw a tension. Remember, ropes always pull. You can't push with the rope, so it has to pull. And it looks like that, right? And if you want to, you could even extend the line, and realize that, oh, this is a 30-degree line, right? It's 30 degrees from the vertical, if you want to. Okay. Now, if you're savvy at this, you should always be thinking this one thing. Always be thinking here. And that is, remember, you can't solve more than 3 unknowns. I already have 3 unknowns right here. So when you look at B, you go, oh yeah, it's touching B. And you could say, oh, well, there's a normal force at B perpendicular to the surface. The problem with this is I already have 4 unknowns. Look at that. That's 4 unknowns. AX, AY, P, and NB. Right? That's 4 unknowns. So what's wrong? Can I get rid of any of those? What's that? Oh yeah, by the way, I haven't put this down. You're right. I mean, the last thing I should do, I always look at where everything, here's how I draw a free body diagram. Where is everything touching? And it looks like it's touching in A, B, and C. And then the second thing, is there any weight forces? So where is it touching? Where's the weight force? Well, obviously, as you mentioned, you're correct. There's a weight force right there at G, and it is 200 pounds, right? This is point G. Of course, right here is point C, right? This is point B, of course, and this is point A. So the problem is, okay, go ahead, yeah. That is correct, okay? The problem is that anytime you see this, it's an absolute rule. You cannot solve this free body diagram as shown. Impossible, totally impossible, okay? So you cannot have 4 unknowns. You can't have 4 unknowns. You can only have 3, okay? And so, yeah, the question is now, can we think about this? So it says, determine the force in the cable in order to lift the 200-pound ramp. Well, if the ramp has been lifted just a little bit, right? Just the tiniest bit, if it's been lifted, well, is it really touching that B? No. Yeah, so that's why we can get rid of it. We can get rid of it because we can say, oh, no, it's been lifted, okay? And honestly, that's the kind of thing you'll see in some problems. Not every problem, but in some problems, you will see that. You will have to think about this, okay? And I know that you'll get stuck sometimes because you'll go, how can I have 4 unknowns? Something's not right. You have to look at the problem, you have to think about it and go, oh, well, there's no force at B. If it's being lifted, there's nothing at B. Because as soon as you lift even 1/10 of a degree, even one little bit, right? Even if you, just tiny bit, well then, there's no force at B, right? You could lift it a millimeter off of the surface at B. How could there be any force? It's not touching anymore, right? So we basically get rid of it, right? We just get rid of it. Now can I solve it? Yeah, right? So that's a great free body diagram, okay? But you realize that 1, you got to be able to do the basics of just drawing the forces, and 2, sometimes you got to be able to think about things. I know thinking's hard, but sometimes you got to do it, and then when you do it, you go, oh, that's it. Now, the rest of this is a piece of cake, at least to me, and that is some forces in some moments, right? So we write out our equation here. Sum of forces in the x direction, where I'm going to say right is positive, as I usually do, right, equals 0. That's one of my basic equations. Sum of the forces in the x direction equals 0, right? Right. So what do I got here? Well, if you look at this, obviously I've got AX. That's easy. AX, that's easy. That's just in the x direction. And then you'll notice that the tension in the rope, right, the cable or whatever at C, has a component in the x direction. And if you think about it, it's obviously positive x direction, I think, right? I mean, it's going to the right. And if you think about it, right, I think you'll see that it's t sine 30. $30, right? I don't think there's anything else in the x direction, right? Those are the only 2. How about y? That should be easy, right? Sum of forces in the y direction. AY, that's always the easiest. AY. If you have t sine 30, you must have t cosine 30. And that's also up, right? The tension's pulling it up. So plus t cosine 30 degrees. And then don't forget the weight force. All right? Good. So those 2 equations should be pretty easy to write. Now the last one is a moment equation. okay? The last one's a moment equation. In this case, what do you want to sum moments about? Probably A, B, I don't know, B seems hard. A, I like A. Why A? Because you have two unknowns at A. Anytime you have multiple unknowns at a point, that's a good point to sum moments about. So I'm going to do A. Makes it easier. Some of the moments about A always, how I do it is counterclockwise positive equals 0. Now, in order to help things a little bit, I'm going to do this. You don't have to do this. I'm going to do this. See that T there? I'm just going to be explicit on that T. And I'm just going to do this. You don't have to do this. I'm going to do this. I like to do this. I'm just going to write these explicitly out and go, you know what? That one right there, that's T cosine 30 degrees, right? And you know what this one is right here? That's T sine 30. Why am I doing that? Because it's going to help me. It's going to help me see things, okay? Because I have to be careful here, right? So let me write out the moment equation here. We basically have two forces that create moment about A. The tension, right, and the weight force, the 200 pounds, right? But really that tension in the cable has two components as I've drawn them. The vertical, the T cosine 30, and the horizontal, the T sine 20, right? So it'd probably be better, in my mind, maybe not yours, but in my mind it'd be better to just go right to the components and then look at those. So, for instance, take a look at T cosine 30, the vertical, okay? So, I'm going to write T, make this small, T cosine 30, right? What's its perpendicular distance to A? What we're really asking, I'll draw it on the picture. What we're really asking is this. We're asking this distance between C and A straight across, right? We're asking for that distance, which maybe it'd be better if I drew it here. Right? We're asking for this distance right here. Straight across distance. What would that be? The straight across, the horizontal distance between point C and point A, right? Because that's the perpendicular distance between the vertical T cosine 30 and point A is the horizontal distance across, right? So what would that be? Yeah, 9 cosine 20, yes. Because if you look inside here, right, there's a triangle here. It's 9 this way, and then we don't know what these other are, but this is a 20-degree angle, right? So this is 9 feet, right? So once you see that, you're like, oh, 9 cosine 20, right? Yeah. These are a little harder because you notice I have a component of not only the force, but a component of the distance. So these are a little trickier. Last thing is, does this vertical force, the T cosine 30, does that create a clockwise or counterclockwise moment about A? Just the vertical. It looks clockwise to me, right? Do you see it? Just the vertical is going clockwise around A, right? Because if you draw it like this, it looks like just the vertical's doing this, right? So I think that's clockwise to me. So that's negative. So I put the negative. Okay. What about the other force? Well, once you get this one, the other component should be pretty easy. The T sine 30, right? Because what you could do is you could go, okay, T sine 30 degrees. What's its perpendicular distance? Well, then it's how the height difference between the two. which if you look at the green triangle is 9 sine 20, right? And then is that a clockwise or counterclockwise, the horizontal? Horizontal force around A. I think it's counterclockwise, right? If you look at it, isn't that kind of turning A counterclockwise? So I think it's plus. And then lastly, we got the 200-pound force. Don't forget about the weight force. Its perpendicular distance. Well, if you've already done the green triangle and understand the green triangle, well, then doing the other one should be easy because now you're just, instead of going C to A, you're going G to A. So instead of it being a 9-foot triangle hypotenuse, it's a 6-foot, right? So it's the same idea. In this case, it's 6 cosine 20, right? And I think you'd realize if this is going down, it is also going counterclockwise, right? So if you do all that and you sum to 0, okay? Now the question is, how are you going to solve this, okay? Can you solve it? Because you have 3 equations, 3 unknowns. I hope you can, right? What you could do if you wanted to is set up a matrix. I don't have all the numbers in front of me to set up the matrix, but you would set up a matrix like this, and you would have the unknowns, let's say AX, AY, and T, for instance, and you would do something like this. I could certainly look at that top equation, and I could write it for you because it would be this. It'd be 1, 0, 0.50, right? Because sine 30, if you look at the sum of forces in the x direction, look at the sum of forces in the x direction. It's AX plus T sine 30 equals 0. Well, sine 30 is half. I know that one. So that's going to be 1, 0.5. That should work that out, right? And the other one's not that bad either. It would be this, 0, 1, and then T cosine 30. I know cosine 30 is square root of 3 over 2, so it would be square root of 3 over 2. And this would actually be the 200 on the other side, right? Because if you look at the y equation, you have to bring the 200 to the other side. Now, the other one, I can't write that. I don't know what that is. I don't know what that is. I don't know the bottom one. But you could, figure it out. You have to calculate it down. And then you could solve it that way. Now, it turns out if you do, you get a tension of 195 pounds. So it turns out that that cable has to pull 195 pounds, initially at least, in this position, in order to lift the ramp. Okay, that's good. Because if I had a motor or something like that, if I had to, if I had to spec out a motor to lift this thing, and I was designing a system to lift the ramp, I would know that I'd have to have enough torque to generate a force of 195 pounds on that cable. Okay, so then I'd figure out the motor I needed, place the motor, power it up, and then hook it all up, and then run it and lift the ramp. Now, obviously, I probably want a little factor of safety, right? I wouldn't want the motor to be able to only generate 195 pounds. I probably want to generate a little more. But probably not too much, right? You wouldn't want to go jerking the thing too fast, right? Probably don't want to design it to do 500 pounds, and it goes, So, or at least you have to control it. Then you have to have a controller, what we call a drive system on the motor. So, but that's a whole other thing. You do that later. Okay. Right now we're just like, okay, what's the statics then? Statics say I have to get at least 195 pounds. The key thing I wanted to show you here, again, is that if you don't do this right, you get stuck. Because if you draw a force at B, you're totally stuck. Okay? All right, how about this one? We'll go through these a little faster. We're just going through examples. I feel like you probably need some of these. This is so critical, you probably need a few examples. Determine the necessary counterweight in order to keep the 200-pound man up there in the bucket with center of gravity G2. Notice he's kind of leaning over, right? This is like a worst-case scenario. This is some kind of device maybe to raise somebody up. Maybe there's like a motor that raises and lowers the bucket, right? Some kind of device that raises somebody up. And we know there's a possibility that if you raise somebody up like this, looking at the structure, I mean, he could tip over, right? So we put counterweights there at B on the other side to obviously keep that from happening. So it says determine the necessary counterweight at B in order to keep the 200-pound man with center of gravity from tipping. The structure weighs 120 pounds and center of gravity is G1. Now, again, we probably wouldn't want to design it this way. You don't want to design it right at 200 pounds. What if he had a big breakfast in the morning and he weighed 201 pounds, right? You don't want to design it like that, right? You want to design it where you have plenty of extra, right, before it tips over, right? But you could see in this case it's kind of a worst case scenario because notice how far G2 is to the right. Like he's really leaning over, right? So he's really leaning over, but we're still trying to prevent it from tipping, okay? So you go, how do I do that? How do I solve this problem? Okay, well, free body diagram, right? Free body diagram. So how do I draw this thing? Do I have to draw everything? Well, not really. You draw it like this. You sort of have to draw the bucket, I guess, just because you have the force there, G2, right? And you got a G1 here. Okay. And then that, do you have to draw the tires? Not really. Okay. So that's probably good enough right there. So it says here the structure weighs 120 pounds, so I'm going to put that at G1. The guy weighs 200 pounds, so I'm putting that at G2. We don't know how much force here WB is. I'll put it like that. I don't know how much force is on the wheel, right? The wheel hits the ground at C and D, right? And so I'm going to call this FC. And then the wheel hits the ground also over here. I'll call that FD. Right? You see anything I'm missing? You always look at where's it touching ground? Well, there's only two places touching ground, C and D. So I put forces there. And then are there any weight forces? Yeah, there's several weight forces. There's a weight at B, there's a weight G1 and G2. So where is it touching and are there weight forces? Those are the two things you've always got to ask when you draw free body diagrams. Where is it touching? Are there weight forces? So how many unknowns do I have here? How many unknowns? It should be easy, right? Look, count the unknowns in the free body diagram. 3, right? So I should be able to solve this, right? I think, right? Yeah, we would think so, right? But there's a problem. Notice I have 3 equations. I always have 3 equations. Right? And then sum of the moments about some point. Boy, in this case, I'm not sure what point I'm going to sum moments about. I don't know. C or D makes the most sense to me. Okay? So sum of the moments. Notice I have 3 equations, right? But in this case, do I really have 3 equations? What about that first equation I just wrote? Do I really have this equation in this problem? Not really. Why don't I have that equation? I mean, I do. But what is it? Let's write it out. Sum of the forces in the x direction equals 0. Where's my x direction forces? What forces do I have that are in the x direction in my free body diagram? Nothing. So what is that? I mean, that's not real. I mean, 0 equals 0, right? So do I really have an equation? No. If you don't have any forces in a particular direction, like this, you don't really have that equation. Which means, unfortunately, we lost an equation. Not because it doesn't exist, it's because it doesn't apply. There's no forces there, right? There's no forces in the x direction. Now, some of you might be saying, what about friction on the tires? Aren't there friction on the tires that would keep the... Yeah, you're right, but we're not in friction yet. So the good news is we're not in friction yet, so we don't have to worry about it, okay? It's not there yet. So in the light of this and the fact that I lost an equation, is my free body diagram now solvable? I thought it was. 3 equations, 3 unknown. But one of my equations doesn't really exist. So now I have 2 equations, 3 unknown. What do I do? Well, this is probably similar, right? We have a similar argument to this one in the previous problem, right? What's the similar argument here? What can I eliminate based upon the structure of the problem and what I'm being asked? This is what you got to think. Yes. Why? Yeah, exactly. Yeah. So it's the same idea, same logic that we just did sort of on the other one, where the other one said, well, if it's about to lift, then there's no contact. In this case, if it's about to tip, like you've been in situations, I'm sure, at some point in your life where you're on a structure. Hopefully it's not a high structure, right? Maybe you're on like a short structure, right? And you're about to fall over, like a chair or something like that. You know, you tip back your chair, right? You know there's like a point where you're about to tip, and you're like, whoa, I'm going to lose it, right? And so if this thing is just about to tip, what happens at sea? The wheel lifts off the ground, right? Just ever so slightly. It might be like a millimeter off the ground, right? It might just be a millimeter off the ground. But if it's about to tip, then there's no force at sea. If it's about to tip, there's nothing there, right? So that's how you have to do this. Unfortunately, or fortunately, really, right? You have to think about these things sometimes, right? Because you can get stuck if you didn't realize that. Okay, you have to think about this. If it's about to tip, there's nothing there. And if there's nothing there, we just take it out. And now can we solve this? Yeah. And in fact, if you look at this, you don't really even need to write the y equation, okay? I will tell you this as a hint to you. Typically, moment equations are your most powerful equations, okay? Moment equations are your most powerful. Now, the force equations are the easiest to write, but the moment equations are your most powerful. In this case, there's a very powerful moment equation. If I want to solve for WB, where might I want to sum the moments about, now that I got rid of the force at C? If I want to solve for the WB, this counterweight force at B, where might I want to sum the moments from? To make it easy. You can sum the moments anywhere you want, honestly, but to make it easy. Come on, we got to be more awake than that. Somebody else has got to answer this.
D?
D. Yeah, because it's an unknown. Yeah, D. Yes, good. D. You know, because this point right here, right? Some of the moments about D. You all should be able to do this. This should be super simple, right? This is not hard because all the forces are vertical. There's no weird forces or anything. This is very easy. Some of the moments about D equals 0. If you look at this, you'll notice the counterweight WB does create a positive moment about D. It sure looks like it's counterclockwise. And what's its perpendicular distance to B? Don't say 6 feet. It's 7. Yeah. WB times 7 feet, right? How about the 120? Boy, the 120 at G1, that also looks like it's a positive moment, right? And if you look at it, you got 120 pounds. Ooh, doing it again. Come on. 120 pounds. Times, that's 1 foot, right? 1 foot And finally, the guy in the bucket minus 200 pounds, because it's going to be a clockwise moment, as you can tell there. And then it's the distance over on the bucket. If you look at the top of the bucket there, it's 2 feet. Right? That's an easy equation. It turns out WB, if you solve it, is equal to 40 pounds. If you weigh 200 pounds, though, exactly 200 pounds, and your buddy said, I did the calculations, here's 40 pounds counterweight, I don't think I'd be too comfortable going up there, though, right? I'd be like, why don't you throw a few more stacks of weight on there, right? I wouldn't do 40 pounds. I'd be like, why don't you throw 80 on there? Let's just be double careful, right? Throw an extra 40 on it just to make sure I don't tip over and die, right? So, yeah. So that's just the limit. That's the static says this. You know, the reality is I would probably do a lot more, right? But the static says that. And it's good to know the statics, even if I was doing reality, because, you know, even if I was like, you know, if I didn't know the statics, I'd be like, I guess I better throw a ton of weight on B. I'd probably put hundreds of pounds on B, just to be like, I don't know, I'll put a lot on it, right? But you know the statics, you go, well, it's supposed to be 40, I'll put 80, should be safe. You know? You could calculate what it took. In fact, you could change the weight of the guy from 200 pounds to 300 pounds, and then see what it is. You could, you know, say, okay, well, I don't weigh 300, so therefore, you know, I know it's safe. You can have a more logical answer to it. Okay, so we keep going through here, and we're going to take a look at another one here. So this is an interesting problem because this problem really demonstrates that you can draw a proper free body diagram and still not be able to solve the problem. And sometimes there are multiple ways in which you can draw a free body diagram, and some ways in which you draw it just don't work. And you bang your head against the wall and you go, this should work. I drew a proper free body diagram. Yeah, you did. It's just still not solvable. Because sometimes there are multiple ways to draw the free body diagram, and you have to think about it. And again, that's hard, right? Thinking's hard, okay? So take a look at this problem. It says a device, okay, is used to hold an elevator door open, has a spring. So something like a spring-loaded device with a little wheel there at the, that is in contact with another part, probably of the fixed elevator, okay? And so, or maybe the other side's fixed, whatever, it doesn't matter. But we have this device, and it has a spring with a constant K, okay, of 40 newtons per meter, all right? All right, and you can see the spring right there. It says it's compressed a distance of 0.2 meters. So actually, once you know the K and you know how much is compressed, you know the spring force, right? You actually don't really need to go further. You can say, as far as the spring goes, the force of the spring is equal to K x minus x naught. Well, in this case, the K is 40 newtons per meter, and the compressed distance is x minus x naught, so that's 0.2 meters, 20 centimeters. So if you multiply these two together, you would get 8 newtons. Okay, so we know the spring force is 8 newtons, and it's compressed, which means anytime you compress a spring, you think about it, that spring is pushing on both ends, right? If you take a spring and you compress it, what's the spring doing to you? It's pushing both of your hands. It's not pulling your hands. Now, if you take a spring and stretch it, right? If you stretch a spring real hard, the spring is going to pull you back in. But if you compress a spring, it pushes, right? So we know that this force has to be a push, not a pull, okay? Now, So we look at this thing and we go, okay, determine the reactions at A and B. It says determine the reactions at A and B. Okay. Well, it sure looks to me, and I'm going to draw an outline of this, it sure looks to me like this is what I would draw a free body diagram. Because I look at this thing and I go, wow, there's a lot going on here. But I'm going to try to draw an outline. I see this shape. Maybe you do too. Right? I see that shape. It looks like that's like a bracket, some kind of piece, right? So let me draw it. Okay. Something like that. Right? There's point A, point B, right? And you could see clearly, hopefully, that the spring has to push down here with a force of 8 newtons. We just solved that. And that's about where it is on the bracket, right? And by the way, we know this distance, right? We know this distance here between A and the spring force is 150 millimeters, right? 150 millimeters. Why is it doing that? All right, 150 millimeters, we know that. Once I do that, I have to go thicker. It's the only way it can recognize me. All right. Okay, 150 millimeters. We get it. I don't know. Okay. And then we know the other side, too. Hopefully this will work for me. Between here and here is 125, right? So, doesn't it look like A and B are pinned? A is pinned. B is pinned. Right? Yeah, I don't see any difference. I don't see, yeah. So A and B are pinned, right? So here's how I draw it. AX, AY, BX, BY. There's my bracket. Now, by the way, I don't have any information about how much that bracket weighs. Nobody told me how much mass it has. Nobody told me how much it weighs. So I'm assuming it's small. It's probably just a fairly thin piece of metal. Probably not that big. So I'm going to ignore the weight. What's the problem here? What are my unknowns? My unknowns are AX, AY, BX, BY. 4 unknowns. Oh, man. You should know by now that that doesn't work. So am I stuck? I go home? I give up? No, right? Something must be. Did I draw the wrong free body diagram? Is there anything wrong with that free body diagram? Not really. I promise you there's nothing wrong with that free body diagram. Nothing wrong. I just didn't draw the right free body diagram. That's the problem. And that's a frustration sometimes for students. I can tell you this, and you will have problems like this. We will do more problems like this, and this is very frustrating for students, but that's life sometimes when you analyze systems. You can draw a free body diagram, and it's correct, but it's not the best free body diagram because you can't solve it. We can't solve this. This is unsolvable. It has 4 unknowns. Now you could say, could you maybe solve some things? Yes, maybe you could solve some things. I don't know. In this case, I don't know. You could solve moments about A or B, but you still can't really solve it. Yeah, I don't know what you could solve. I don't think you could solve anything. So we have to rethink the free body diagram. Now, here's how you do it. We have to rethink the free body diagram. Yes, AB there is a nice bracket, but that does not mean that that's the only free body diagram you could draw. What about the wheel at B? What if we redrew this free body diagram like this? I'm going to draw that shape again. Right, like this. Ooh. Something like that. Okay. What if I added the wheel? And what if I made that the combined free body diagram? Can you do that? Heck yeah, you can. What if I made the combined bracket AB and wheel one body? There's nothing wrong with that. You can combine bodies and make them like one body. Okay? You can combine two bodies and make them like they're one. Okay? Like this. Okay? So, here's your point A. Do you still have forces, AX and AY? Heck yeah, right? What about B? Well, now that point B is what we would call internal to the system, right? You don't look at point B anymore because it's inside. It's internal to the system. If you combine the bracket and the wheel, then point B is on the inside now. You don't look at point B anymore. It's on the inside. It's internal. You don't have to worry about it. What you have to do is say, well, what's touching the wheel? Well, that other piece there, right? But we know that what's touching the wheel, it would have to be, I'll draw it on the original picture just so you can see it, right? I'm going to draw it on the original picture. I'll draw a different color here. Let me get a different color. Original picture, different color. Here, like this. We know it's going to be something like that, right? Because it's perpendicular to the surface. It's bearing against a surface. If it ever bears against a flat surface like that, pushes against a flat surface, it has to be perpendicular to the flat. And because it's a wheel, we know that that has to go through the center. No matter how you turn it, when a wheel pushes against it and has that, you're going to have it go through that center. So what that's going to do here for my free body diagram is it's going to take this force here. Maybe I could have made that better. Let's try that better. Right? Like this. Force F, whatever you want to call it. Now can you solve it? Yeah. Three equations, three unknown. You see that? And by the way, this force F has to be 30 degrees because it's tilted 30 degrees, so it's got to be here. Got to watch this carefully here. But this would be, if you have a perpendicular, this is perpendicular here, and this is 30 degrees here. So you could figure it out if you needed to. You probably do, because what are we asking for? Oh, yeah, the reactions at A and B. Okay? Now, you might be asking yourself, how the heck am I going to get the reactions at B? They're internal. But here's the deal. Once you get this free body diagram like this, Is there any reason why you couldn't go back to the original free body diagram and solve for A and B, Bx and By? No. You use this free body diagram to solve for Ax, Ay, right? Free body diagram number 2, right? And then we go back to free body diagram number 1 and solve for the other ones. Yeah. So what do we do here? Well, probably what you could do in this case is sum the, let's see here, sum the forces, sum the moments about A in our free body diagram number 2. Sum of the moments about A equals 0. Right? And if you do that, then you've got this force here, which maybe I'll move up to B. There's no problem with moving a force on its line of action. So you could do this, right? And then with this force F, let's see here, it would have to be, if it's perpendicular to that line here, then kind of need to draw this better. Here, let me draw this back because I want to make sure we get this right. If it's perpendicular to the 30 degrees like that, then I think then this is 60 degrees here. I'm pretty sure that's right. So, is that right? No. Yeah, that's right. That's right. Yeah, that should be right. Because this would be 36. Yeah, that's right. Yeah. So we would do it like that. And so then, if you want to sum moments about A here, oh, don't forget about the original spring force. The spring force here is 8 newtons, wherever it hits, something like right here. So if you want to sum moments about A here, what do we have? We have force F has 2 components, a vertical force, a vertical component, and a horizontal component. And so I would probably write the horizontal one. It's going to be F cosine 60 degrees times its perpendicular distance, which is up, which is going to be the, I'll write it as 100 millimeters. You could write 0.1 meters too. And then that's going to be negative, because that looks like it's clockwise. You've got plus F sine 60 degrees times its perpendicular distance all the way across from B to A across. If you look at the top there, it's 150 plus 125, so that's 275. And that's a positive moment. And then finally you got one more moment that appears to be negative clockwise, and that's going to be the 8 newtons times its perpendicular distance, which is the 150, equals 0. So you can go on all that and solve for F. Turns out you get F as equal to 6.38 newtons if you solve for F. Now that's not the answer, of course. But then you can go ahead in this original picture, you can solve for AX and AY. I'm going to skip the details, but you solve for AX and you get 3.19 newtons, and you solve for AY and you get 2.48 newtons. And then what you can do is you can then go back and solve, now that you've got both AX and AY, you can easily solve for BX and BY in the top picture. Why? Because look at free body diagram number 1. If I tell you what AX and AY is, BX and BY are trivial. In fact, BY is exactly the opposite of AY. Right? BY is equal to negative AY. So BY has to be equal to minus 2.48 newtons. Because they're the only two, oh, sorry, I'm sorry, and there's 8 newtons, I'm sorry. I meant BX and AX. BX and AX are, BX is minus 3.19, because those are the only X direction forces. Y, you have the 8 newtons down, too. So you have to adjust that. But you could write those out. Okay? Last one. I think this is a fun one to try to do on your own if you can get 3 identical books. Okay? If you can get 3 identical books, what I want you to do, what we'll do, since we haven't had a little extra credit in a while, is if you can do this for me. Here's your thing. Okay, I'll make a little Dropbox for you. Okay. What I want you to do is I want you to solve this problem, but you have to solve the problem by actually showing me 3 identical books and doing this. Okay. So what you need to do is you need to get 3 books. They have to be identical. That's the hard part. You got to find 3 books. Go to a library or something like that, right? And find 3 books that are the same size, shape, and size, right? And what I want you to do is show me a picture. Take a picture with your phone, whatever, right? And show me the setup and say, yeah, I did it, and I proved to you. And then I want you to also show me the statics, the picture and the statics, okay? If you do that, I'll give you a bonus, then we'll add to the quiz, like 3 points to a quiz, okay? We'll add 3 points to your, lowest, I don't know how we do it. 3 points to your lowest quiz or something like that, sure, okay? So we'll do that. We'll basically add 3 points to your overall quiz score at the end of the semester, put it that way, okay? So whatever your quiz score at the end of the semester, we add 3 before we, it won't, you'll always add 3 no matter what, okay? If you can do this. But you have to show me a picture of the books, 3 books, show it in that position, because obviously they have to be leaned over, and then you have to show me the statics to prove that. Not that hard to do. You can do it, okay? I'll open up a little Dropbox, and you can do it on your own as a little exercise, okay? I always think it's kind of fun. So it only takes 3 books to do it. So anyway, we'll do that on your own, and we'll see you next time.